Hey guys, it's me, and I just have to tell you I'm really excited to talk about the transition metals with you. So for those of you that need some reminding, your transition metals are the elements in the D block. So families 3 all the way through family 12, and sometimes tin and lead are also considered transition metals. We'll talk about that a little bit later. All right, so here I've written the electron configurations for all of the transition metals in period 4. So going from scandium all the way to zinc. So we're just going to talk about those as our examples for what transition metals will do. All right, so I have written these electron configurations a little bit different than you've seen it. I went ahead and put the S block after the D, or the 4S after the 3D, even though if you were to do it, you would have the 4S in front of the 3D. And I did it just so that you can kind of see a pattern here. So from electron configuration, hopefully you noticed that the outermost energy level on all of these elements, because they're all in the same period, is the 4th energy level, and that they all have 2 electrons in their outermost energy level, which would mean that by electron configuration, your transition metals appear to have 2 valence electrons. But what makes transition metals really interesting is that transition metals are elements that have D sublevels, these D sublevels in the energy level below their outermost energy level. And they're able to actually use those D electrons as valence electrons, which essentially means that they're capable of using the electrons in their 2 outermost energy levels as valence electrons. So why can they do this? They can do this because their D and S sublevels are very close in energy amount, which means the electrons that are contained within them are close enough in amount of energy that they all essentially act like their outermost electrons. So what this all boils down to is the fact that transition metals have or can have a variable number of valence electrons. So unlike your families 1 and 2, and then all of these families 3 through 17, who have pretty set numbers of valence electrons, your transition metals are kind of all over the place. So we're going to talk about why, and I'm going to give you some examples. All right, so let's talk about iron first. So iron is, if you look at its electron configuration, it has 2 electrons in its S and 6 in its D sublevel, like this. So iron has there are 2 things that iron can do, or 2 more common numbers of valence electrons that you'll find in iron. The first is that iron is going to just use these 2 as valence electrons and end up with a charge of +2 when it loses those. And then its electron configuration would end up just like it is over here, argon, and then the 3d6 that are left over. And then, of course, the 2 S electrons are gone. So that's one thing that iron can do. Another thing that iron can do is end up using 3 of its S and D electrons. And so what it ends up using is these 2 S and this 1 D. So its orbital configuration is going to end up something like, instead of those 2 electrons, there's only going to be 1 left in there, and then it's going to lose those 2 and 1 of those and end up with the electron configuration of argon plus 3d5, which means that it's got a d orbital that is exactly half full. There's exactly 1 electron in every orbital, and this is considered extremely stable. So you'll find with iron, these are the 2 most common ways that iron will ionize. And that's some typical transition metal behavior. All right, let's do another one. Let's talk about chromium here. So if you look at chromium, chromium has, according to electron configuration, has 2 electrons in its s and then 4 electrons in its d, and you'll notice there's this open d orbital. So what chromium can do is use these 2 s electrons right here and end up chromium with a +2 charge when it loses those electrons. And so its electron configuration would end up argon and then 3d4, right, because you're losing these 2 valence electrons. But what argon, or rather what chromium actually does more often than that, is it will take one of these s electrons and put it into its d sublevel. And so it ends up removing or taking that and moving it up to here so that it has 1, 2, 3, 4, 5, remember, our half full 3D sublevel, which is really, really stable. And then that means it's only got 1 valence electron in its 4s sublevel, and so it's going to end up forming a chromium with a +1 charge by losing that 1 s electron. And its electron configuration would then be, after it loses that, argon with 3d5, just like that iron with a +3 charge that had the 3d5 as well. So that being said, chromium has at least, from this electron configuration, 2 possible ion charges, and can actually have more than that, but we're just, doing some examples. So what I really want you to take away from this is that your transition metals have the possibility of having variable charges, more than 1 possible charge on their ions. And I want you to notice that all of the ion charges that I've shown you have been positive because these are metals, and that's what metals tend to do, is lose their valence electrons. And because each of these transition metals has d and s electrons that are so close in energy that they are all considered valence, they have a number of different options of numbers of valence electrons that they can lose to form different charged ions. Now, there are, of course, some transition metals that have only 1 set charge. And there are a number of them, but I want you to just know a couple. And so let's talk about scandium. Scandium's electron configuration has 1, 2, 3 valence electrons possible. And scandium tends to just lose all of them. So it ends up losing all 3 of those electrons and becoming scandium with a +3 charge, and its electron configuration just ends up that of argon, which we know is a noble gas and of course very stable because it has a full outer energy level. So scandium, this is basically, it's an exception, right? This is the only thing that ever happens to scandium. And so you need to remember that scandium always has a +3 charge on its ion. And the other notable exception is zinc. So let's talk about what happens with zinc. So if you look at zinc, zinc has a full energy level, or D sublevel. It has 10 electrons in its D sublevel, and that's completely full. So it's not going to want to really give up any of those 10 valence, or those 10 electrons as valence electrons. So that being said, it's only ever going to give up its 2 s electrons and end up with a +2 charge and the electron configuration of argon plus 3d10. So this is the only charge ever on zinc, is a +2 charge. And the last exception to the varying number of valence electrons is silver. So if you look at silver's electron configuration, it's that of krypton plus 5s2 and 4d9. And it is so close to having that 4d9 level full that what it's going to do is it's going to move one of its s electrons into that d sublevel and make it 4d10 5s1. So then it only has this 1 electron in its s sublevel that it will use as valence. And so silver ends up forming silver with a +1 charge by losing that 1s sublevel electron. And then it keeps, of course, the electron configuration krypton and its 4d10, which is very stable, remember, because a full D sublevel is really, really stable. At the beginning of the video, I told you also that tin and lead are capable of forming varying charges, so they act like transition metals in this way. And so, let's just talk about that briefly. So they're both in family 14, which means that they would have 4 valence electrons. And since they are metals, they would lose those valence electrons typically, right? And end up both of them having a +4 charge. But for whatever reason, which I'm not going to get into, they are also capable of only losing 2 valence electrons. And that would make them have 2 or a +2 charge. So those are really common things for tin and lead specifically to do. So you're going to see that happen, and I just wanted to make sure that I mentioned it. So for you, what this is going to come down to is how are you going to know? Because I'm not going to expect you to remember the different ways in which the transition metals are capable of switching around their D and S electrons. I will expect you to remember that scandium, zinc, and silver, and tin and lead, what their charges are. But everything else, all the other transition metals, how are you going to know? The first way is you're just going to look at the name of the compound. So you'll notice this is typically how you would name a transition metal compound. Copper, and then a Roman numeral 2 in parentheses, chloride. This Roman numeral 2 indicates the number of valence electrons, and then of course the charge on that copper. So what you're going to find is the copper in that compound has a +2 charge on it. And so that's what that Roman numeral tells you, is that it's got 2 valence electrons that it loses, so it's got a +2 charge. As opposed to something like, say, copper 1 chloride. Copper 1 chloride only has, or the coppers in it have a +1 charge. And that's going to make the way they bond to the chlorine very, very different. Because, if you remember, maybe you don't, but I'll remind you, chlorine is, in family 17, it has a set charge, which is a -1 charge. And so if you look at the charges on these two ions, copper 2 versus copper 1, when these two things bond together, for copper 1 chloride or 2 chloride, when you cross the charges to write your formula, you're going to end up copper bonding to 2 chlorines to make a neutral compound. Whereas in copper 1 chloride, where the copper only has a +1 charge, if you were to cross the charges down to write the formula, you're only going to get 1 copper to 1 chlorine, and that's a different compound than copper 2 chloride. The second way that you might know the charge on your transition metal is by looking at what it's bonded to, so looking at its chemical formula. So here's a typical example, Fe2O3, which by the way happens to be the chemical formula for rust. In this compound, you have 2 irons bonded to 3 oxygens. And, oxygen has a set charge. its charge never changes. It's in family 16. It always gains 2 electrons and always has a -2 charge on it. So if you look at how many irons you have and how many oxygens you have, you should be able to figure out the charge on your iron pretty easily. So if you have a total of 3, oxygens, and each of them has a -2 charge, that's going to add up to -6 total negative charge in this compound, which means that our irons have to add up to +6, so that when we add these two things together, it's going to equal 0 or neutral, right? Because we want our entire compound to not have an overall charge. So the only way for that to happen is if your irons each carry a +3 charge. So if you add 2 of those together, you're going to get your +6 that'll cancel out your -6. So in this particular case, your iron has each of your irons has a +3 charge. So if we were going to name this compound, we would name it iron 3 oxide to show that the irons in this compound have a +3 charge. Now, easy way to do this, of course, is to just uncross your charges like this. But sometimes that doesn't work, so don't use it always. But if you uncross the charges, then of course you're going to end up with the Fe with that +3 and then the O with the -2. So that's kind of a cheater method, but it works about half of the time. All right, so that concludes this tutorial on your transition metals.